All right, so we're picking up right where we left off, and we said, okay, we have these two different ways of writing imaginary numbers. We have the rectangular format and the polar format, and we want to be able to go between the two. Now, it's not as challenging as you might think to go between the two. So I'm going to first draw in here some blue lines here. And what I've basically done is I've formed a right triangle. But if I think here and go back to kind of my notation A and B here, and ZM, I labeled the hypotenuse of that triangle as ZM. But if I think of here as the base of this triangle, well, that's how much I'm going out in the x direction. So really that is A. And then if I think about, okay, well, this opposite of the angle side here, that's how high up I go. So that's really my B. Let me erase this little here so I don't really need that there right now. And so we can come up with some simple equations on how to convert between them. So it doesn't really matter which one we discuss first. So I'm going to go ahead and say let's do polar to rectangular. So for instance, we're going to be given a number in polar format. We're going to be given z equals, for instance, let's just say 10 at an angle of 25 degrees. And we want to know how to convert that to polar. Not polar, I'm sorry, convert to rectangular. Well, let's just develop our formula looking at this triangle up here. So we have given z is equal to some magnitude at an angle of theta. We want to convert this to rectangular format. Well, I'm going to do just some right triangle trigonometry here. So if I look here, for instance, at what the cosine of theta is, and a cosine is adjacent over hypotenuse. So this would be A over Z sub m. And so real quickly I can see if I just multiply both sides by Z sub m, I get A equals Z sub m cosine theta. So I'm going to box this. You might want to write this equation on a separate sheet of paper and just kind of develop a piece of paper with the equations on it so that you don't have to flip through your notes. And then similar, we can do another right triangle trig, and we can look at the sine of theta. And if I do the sine of theta, well, we know that the sine is opposite over hypotenuse, which would give me that B is equal to Z sub m sine theta, doing a similar kind of multiplying by both sides. And so these two equations that I've boxed here are how you will convert from polar to rectangular. So let's go ahead and do that here. So for this example here, if I wanted to convert this to rectangular, A would be equal to 10 cosine of 25 degrees, and B would be equal to 10 cosine, I'm sorry, not cosine here, 10 sine of 25 degrees. And so let's bring up a calculator here. Is this in my scientific mode? It is scientific, but where's all my trig functions? Oh, there they are, trig. Okay, so the other thing you want to make sure is that the mode of your calculator is correct here. So you want to make sure you're in degrees and not radians or anything like that. So to get A, I would do 25 cosine, and of course it depends on how your calculator is used as far as how you'd enter it, times 10. And so I get 9.06. So this would be equal to 9.06. And then we need to do the other one. So I'd have 25 trig function sine times 10. And I get 4-point rounding 23. And in general, I do like either 2 decimal points or have 3 significant figures. And so now I can write that my rectangular form of this, because you want to write your final answer down, the rectangular form is 9.06 plus j 4.23. So as long as we have these formulas, converting from polar to rectangular is actually quite easy. It's not difficult to do at all. Now, I will also tell you that sometimes some of your calculators, depending on the calculator you have, they'll do that conversion for you automatically. But I don't know what kind of calculator you have at home, and I don't necessarily know how to use your particular model of calculator, but you can always look it up in your user manual or just even look it up on the internet. Type in the model of your calculator and then like complex numbers, polar to rectangular kind of, and there will probably be a little tutorial video for the model of your calculator. Now, of course, your calculator you would want to make sure your calculator can do complex numbers, but you can actually even find online calculators for free that will do complex numbers. All right, so now we want to look at how do I convert from rectangular to polar. So I'm going to erase this right here. And so what we're given here, we're going to be given that z is equal to a plus jb. And we want to find both z sub m and theta. Well, we can just use Pythagorean's theorem here and get that a squared plus b squared is equal to z sub m squared. And so then we can quickly see z sub m, and now you might say, well, you get both a plus or minus when you do a square root of both sides, which are correct, you do. But when we're talking about z sub m, we always typically use it just as the positive one, because it makes it easier for us to get the angle correctly. So z sub m is then simply just the square root of a squared plus b squared. And now we're going to go back to some trig here to figure out what theta is. Now, you might say, oh, I'm going to use z sub m. We really want to just use a and b, because that's what we've started with. So if I use some trig here, using another trig function, we can say that the tangent of theta is equal to, well, that's tangent's opposite over adjacent, so it'd be b over a. And then these two equations right here are what we use to find z sub m and theta. Now you might question why I didn't solve this one for theta. Because theta, if I solve this for theta, is clearly the inverse tangent of b over a. But we need to be careful. Inverse tangent only gives answers between negative 90 degrees and 90 degrees. And so we'll go through a couple examples here of converting to rectangular, because polar to rectangular is easy. You never have to worry about making a mistake as long as you use the two formulas correctly. But going from rectangular to polar, z sub m, you shouldn't have to worry about making a mistake. There's nothing wrong with this equation here. But you can sometimes get the wrong angle if you're not careful. And we'll look at a couple examples illustrating that. So let's first just even look at the example here that's going to do the number we just plotted here. So let's look at z equals 5 plus j2. So then z sub m would be the square root of 5 squared plus 2 squared, which would just be the square root of 25 plus 4, which is the square root of 29, which you could leave it as square root of 29, but I'm going to go ahead and do the square root of it, if I could find where that is here on my calculator. Why can't I find square root here? There's squared and cubed. There's got to be a key here to do this. Just a second, I'm going to pause. There it is. I found where it was here now, 29, and I have to hit the second button, and now that's the square root. Okay, so 5.39. Now, I typically will compute the number out because often we're actually wanting to know the number as opposed to square root of 29. I mean, square root of 29 is a number, but I don't know what that is off the top of my head. I know it's 5 point something because the square root of 25 is 5, but I don't know what it is. So typically it's best to write it as a decimal. Now I'm going to go ahead and say tangent theta is equal to b over a, so this is 2 over 5. Now I'm going to actually, even though we've already plotted it once, I'm going to go ahead and plot this roughly again. I'm not going to be precise. I'm going to say what quadrant is z in. And if I plot it here, it's going to be, it was like roughly there, so it's in quadrant 1. And remember, we have 4 quadrants. And the inverse trig only gives us angles in quadrants 1 and 4. So if the answer is that the number is in quadrants 2 or 3, we'll have to do something additional, and I'll show you what we'll need to do. Okay, but since it's in quadrant 1, I can literally just do the inverse tangent of 2 over 5. So let's do 2 divided by 5. Whoops. 2 divided by 5. I don't want to do tangent, I want to do inverse tangent. Oh, there's a second within the menu. Wow, that's silly. 2 divided by 5, second, inverse tangent. And then we get 21.8. So this would be 21.8 degrees. And we do typically write these in degrees. So then I could rewrite this complex number, instead of it as 5 plus j2, I could write this as 21.8, no, sorry. First you do the magnitude, 5.39, at an angle of 21.8 degrees. And then we're done. So let's look at another example of converting a complex number from rectangular to polar. So we have the complex number -j plus -2 plus j3. We want to convert to polar. Well, the first thing I'm going to do here is just kind of sketch where this is. I mean, if you want to be precise, you can be precise, but it's really not that important to be hugely precise on where it's located. But I'll go ahead and be precise here. -2 plus j3. The key thing is this is in quadrant 2. Okay? That's going to be important when we find the angle. And we'll see in a second what's going to happen. But the first thing we can compute, which doesn't matter what quadrant we're in, is of course the magnitude, z sub m, which is just going to be the square root of negative 2 squared plus 3 squared, which will be the square root of 4 plus 9, which is the square root of 13, which of course we can just plug in what that is, 13 square root, and we get 3.61. All right, so that's easy enough to do, 3.61. Now, the next thing here we need to look at is finding the angle. And so if I look here and want to say, well, I'm looking at tangent of theta, and this is going to be equal to 3 over negative 2. Now, if I were to go ahead and just do theta equals the inverse tangent of 3 divided by negative 2, let's see what we get. Well, 3 divided by 2, negative 1.5, of course. And then we're going to do inverse tangent. I get negative 56.3 degrees. But wait a minute, negative 56.3 degrees is not in quadrant 2. Because remember, we always start on the positive x-axis, and then negative means I go clockwise. So negative 56.3 degrees is like right here. And that doesn't make sense at all as far as the angle goes, because we know the angle, you know, if I draw here, this is z sub m, and we know that this should be the angle, theta. So we know theta, I mean, not only do we know it needs to be positive, but it's bigger than 90 degrees, and I'm getting negative 56.3. Well, that's because it's in quadrant 2. So we can actually just simply, to get this, we can notice that, hey, if I were to continue this line down, I'm dotting this line here, look, this angle that I'm getting here is really still on that same line. So all I have to do is actually, to get the correct theta, I'm going to do the inverse tangent of 3 divided by negative 2 plus 180 degrees. And that will get me here, because I have plus 180, I get 123.7 degrees as my angle. Now that makes more sense as this angle here. So then my final answer here is z sub m is 3.61 at an angle of 123.7 degrees. Now on your first homework assignment, you're going to be asked to convert between rectangular and polar because it's critical. Now, even if your calculator can do it for you automatically, I want you to do those computations by hand. You can then, from here on out, the rest of this term, do it using your calculator automatically, but it's important to understand how to do it by hand. Okay, so to end this video, let's maybe talk about how we could, when we're doing rectangular to polar, some people like to have this table. I don't typically use this, but some people like this and they find it useful. So rectangular to polar, z sub m is equal to square root of a squared plus b squared. We know that. And then here what we'll do is we'll make, well, I don't know if I'll make a table here. I'll just say if theta is in quadrant 1 or quadrant 4. And how do you know that? You sketch the plot of the complex number like we just did here. If theta is in quadrant 1, I put is in quadrant 1 or quadrant 4, then theta is simply equal to the inverse tangent of b over a. If theta is in quadrant 2, theta is the inverse tangent of b over a plus 180 degrees. If theta is in quadrant 3, theta is actually equal to the inverse tangent of b over a minus 180 degrees. And you might say, well, why didn't I do plus 180 degrees there? Technically you could, but we typically like our thetas to be between negative 180 and 180. That's the reason I did the minus 180. So sometimes people find this useful, just to have this in their notes or in their list of formulas, so that they still have to plot. You still have to plot where the point is, so you know which one of these formulas to use for theta. But this can sometimes help you, so you don't have to necessarily think, okay, do I add 180 or do I not add 180? It's purely based off of what quadrant you're in. All right, so in the next video, we're going to start talking about how do we do arithmetic operations with complex numbers, because that's what we're ultimately going to be doing. We're going to be using complex numbers in our circuits and doing operations to find currents and voltages.